James Turdar and Samuel Vela. Our project deals with an implantable medical microconnector, and our advisor is Dr. Jones. So millions of people worldwide suffer from a variety of disorders ranging from Parkinson's, hearing loss, to chronic pain. Oftentimes, these are treated with standard therapies such as injections or surgeries, and these could interfere in a person's day-to-day life. So for more severe cases, a better alternative is to use a neurostimulator device. A neurostimulator device is composed of the actual leads and the neurostimulator. The leads are thin wires that provide an electrical signal to the brain, while the neurostimulator generates the pulses. And according to the American Association of Neurological Surgeons, 50,000 neurostimulators are implanted annually. So there is a high need for a neurostimulator device. However, there are various issues related with this device, one of them being a low channel count. This basically means that there's only 16 channels available in commercial use, so this can't account for diseases that require higher stimulation, such as Parkinson's. Also, for the implantable retina, they are currently making over like 300 iodes. Also, this device is hardwired, which means that the interchangeability of the device is very difficult. So, should one part of the component fail, the entire device has to be removed from the body, and this is a problem because nerves grow around the leads. And so when you remove the leads, it could potentially damage the nerves. And finally, this is an electrical component that's going to be placed inside the human body, so we have to ensure that it is hermetic. And now with these challenges in mind, Eric is going to discuss the objectives of our project.
All right, our objective is to create pins in low temperature copper ceramic and high temperature copper ceramic for proof of concept. Make a microconnector with 32 pins because presently there is not a microconnector commercially available. We want to minimize the size. We want to make smaller than the proposed VA design, which in conjunction with them, they are working on developing this technology. We want to make it with biocompatible materials, make it user-friendly for physicians so when they're in an operating room that it's easy to handle. And then also we want to test for continuity and hermeticity. Just to give you a quick materials background, this is low temperature copper ceramic. It goes through a series of steps. It starts off with a green sheet, which as you can see, it's a flux spring material initially. It then goes through a stamping or punching phase, and then we fill it with the materials. Then the next step is the screen printing of the pattern, and then we go to a stacking process where we put the layers on top of one another, and then it goes through a press, and it becomes laminated. Then it goes to the furnace where it sinters, and then it goes to the final step where it's diced up into the multiple parts. Now for high temperature copper ceramic, it's the exact same process except for there's plating for this step number 7. This is fired at a temperature between 1600 and 1800 degrees Celsius. This product is currently biocompatible as it is currently used in the neurostimulator device for the electronic portion. It is also used in a wide range of microelectronics. In addition, HCCC is also referred to as aluminum and has multiple applications. Now, our design requirements that we're looking to achieve is we want to go 32 pin connections, pins on one half, and then vias on the female half, with an O-ring design and a hermetic seal. We want to create a method to maintain the seal. We need to have continuity between the pins and the vias, and then we need to develop a method to attach the wires to the pads, and then we need to develop a strain relief as well. And then for the initial design, Sam Greta.
For the initial design, we came up with several different ideas that could work for the microconnector. The easiest form of connection for anything is a pin in a hole, where the pin slides into a hole, and we came up with a 4x8 pin array with pads on the top side, and also a 6x6 pin array with the pads on the back side, where the wires would be welded to the back side of the microconnector. In addition, we would have to implement a O-ring seal for the design, and as you can see on the circular, we have an O-ring in the ceramic part itself. For the actual proposed design, what we propose to do is a 3x10 pin array plus one on each end, and have the pads, the pads for the wires micro welded to the top side of the actual device. And now, James, to talk about the initial manufacturing.
As mentioned in the objectives, one of the main objectives was to determine the manufacturability of the actual pins using LTCC and HTCC technology. On the right, we see our initial prototype, which shows a 7x5 grid array of pins in LTCC. On the left side, we see the size of the prototype in relation to a dime. And In this manufacturer prototype, we encountered some design difficulties, namely in the manufacturing process during the screen printing. Also, we encountered difficulties in cutting out the groove in the O-ring and ceramic, the alignment of the pins for the connection, and adding a strain relief to reduce the stress on the leads. Now Sam's going to talk about some design adaptations.
Like James mentioned, the screen printing process was very difficult to do in the lab. So what we decided to do is eliminate the screen printing process, which we would have to print on different layers of the LTCC. So that in that way, we located the pads directly on the backside of the ceramic, which simplified the manufacturing process for the microconnector. In addition, we created a housing for the ceramic connector parts. Also, the O-ring was removed from the ceramic part because that was very difficult to achieve and moved into the housing itself, and also a strain relief was added to the housing. So over here we can see how we eliminated the screen printing. The screen printing process would be done on different layers, and it would route the wires to the pads itself. What we decided to do is just go directly to the back of the pads. It's the simplest form for manufacturing. In addition, we created a housing for the ceramic parts to be placed. So over here we have a 4x8 pin array and a housing to place. Also, we have alignment pins added and an O-ring design, O-ring groove added to the actual design. And this was the initial design, and this is what we ended up with the final design, adding the strain relief as well. And now we're wanting to talk about housing.
So for our housing, we would opt to use a mold. This is because a mold is much more precise, and for mass production it's also much more cost effective. However, it was quoted for $10,000 and none of us could afford that. So we decided to show the feasibility of our housing through rapid prototyping. We contacted 2 different companies, Fineline Prototyping and WB Engineering. They both can manufacture parts of micro scale sizes with a very high resolution. However, they quoted only 1/2 of our connector, which is completely really small, for $200. And so that was also very expensive. We also wanted to explore different options for 3D printing biocompatible parts, and you can do this through 2-photon polymerization. With the use of riboflavin, you can make 2PP biocompatible, and it creates a very micro-scale object that can actually be implanted within the body. However, we decided to go with the most cost-effective option, which was using the MakerBot replicator available in Dr. Hazel's lab. So these are the parts that we manufactured using the MakerBot. You can see the actual housing compared to the scaled-up model. Our actual housing, including the strain relief, was 15 millimeters. And here's the updated parts, and the strain relief is now removed, and it's compared to a die. So as I just mentioned, the strain relief had to be separated from the housing. This is because we want to maintain rigidity in the housing in order to protect our ceramic part, as well as maintain flexibility in the strain relief. The flexibility in the strain relief would allow for the leads to not experience stresses in their most vulnerable points. Also, by separating this, we were able to implement the Veteran Affairs design in order to save them money, and they'll be able to use our connector for their devices. And now James is going to discuss the electrical connectors.
So one of the main concerns in doing a project like this is the connections. To make sure we have a reliable, secure connection. Some options that we considered to ensure this is purchasing a micro coiled spring, using a conductive elastomer, and creating a nano springboard in the Amateur Labs. The options that we attempted are the fuzz bundles, as you can see pictured here, the gold bundles of wire. These are used in military applications, so they have a wide background of use, not on the scale, but they can also be bought in biocompatible materials such as tungsten. And also another option that we attempted to use was a conductive elastomer, which also gives flexibility and reliability in the connection. To accommodate the fuzz buttons, which was our prime choice in connection, we had to modify the design as well as the manufacturing process. So in the design modification, we increased the via size to 380 microns on an 800 micron pitch. And we also increased the pin design to 250 micron on the matching 800 micron pitch. To accommodate this design modification, we switched around the manufacturing process just a little bit in this order. First, we punched alignment pins. We cut out the different layers. The layers were then stacked and then laminated. Afterwards, the vias would be drilled with a CNC router instead of using the punch machine. These vias will then be filled with platinum or graphite, depending on the layers, and the graphite is used as a placeholder fugitive material in the laminating process and in the firing process. And then after which the relamination, if necessary, depending on the different parts, will occur. And then the sintering process. The sintering process is where the ceramic is being hardened, after which the parts will be cut out in size. After the parts are cut out in size, the fuzz buttons are inserted and secured with a conductive silver paste or ink, which also adheres to secure the fuzz buttons in the vias. Now Sam's going to add to the final design.
Like Martha mentioned, we would have, the strain relief was selected to be a different material for flexibility and compatibility with the VA clinic design. We also added a silicone band to hold the two halves together. Also, the final design of the final design of our micro connector came to be about 1/2 inch by about 1/4 inch by another 1/4 of an inch. And with the strain relief, the final design increased to a size of about 1 inch. So the final design would then consist of the housings for the two halves for the ceramic parts, boring, the strain relief, and the bands to hold the two halves together. The housing material, we have several different biocompatible plastics that it could be made out of. Also, the strain relief material would be Metacone silicone, as well as the O-ring would also be medical silicone. And over here we have a picture of the male ceramic part. Over here we have the final design that we made with the assembly of the male and the female parts. We added a different strain relief, as well as we added slots for alignment, so there would be no confusion in the direction of which way the pins would be assembled. And over here we have the assembled female half and the assembled male half. And this is how the fully assembled microconnector would look. We have the front view, the top view, and an isometric view. And the exploded view is on this slide, where we can see how the microconnector would be assembled. And these are the drawings of the final dimensions. The dimensions are in inches, so we have about 1/2 inch in length and a 1/4 inch wide with a 1/4 inch in depth. And these are the updated ceramic parts that were manufactured in the Ambry lab. We increased the holes to 380 microns and the pins to 250 microns. And over here we can see the placement of the fuzz button in the ceramic part. And what we have here is updated ceramic parts inside the housing that we had 3D printed. Over here we have the male half in the housing, and we have the female half in the housing. And each of these little points is a fuzz button located in the housing. And for future design considerations, we would add steps to the back of the design. This would allow for a tighter packaging of the wires in the housing, which can decrease the depth required. And now Eric to talk about this.
So in order for our product ever to get used, it has to go through a series of tests. The standard test is military standard 883 for medical devices, medical electronic devices. It's the military standard, and it involves a series of tests: electrical, mechanical, and environmental tests. One of the specific tests that we'd be looking at is test condition 1014. This is the seal test. This is the fine leak and gross leak testing. And then the mechanical pull test, which is to ensure that the wires are securely fastened to the back of the microconnector. And then also we need to conduct a conductivity test to ensure that all the pins, the females and males, are actually properly connected. And then a specific testing protocol would be developed in correlation with the VA in development of this product. So our objective evaluation, we wanted to create pins in the LTCC and HTC. This was achieved after 3 or 4 attempts. The initial unsuccessful attempt, we tried it with the HTCC combined with the LTC, and what happened is the HTC actually responded with the silver and hardened with it, and we were unable to get it off. After a couple attempts, we changed from the HTCC to a carbon, and what happens is once we fired that, the carbon burned off, leaving us with the pins. However, as you can see, the pins aren't very uniform, and they're rather ductile. As you can see in the upper right corner, it was not a straight pin. To alleviate this situation, we increased the diameter and decreased the length. So we made the pin much shorter. It went from 12 mils to 4 mils, and then we increased the diameter from 6 mils to 10, showing the improved pin creation. We also wanted to make the micro connector with the 32 pins. This was achieved, as you can see, in this final design. And then also, we wanted to minimize the size with no sharp edges. This was achieved by doing the circular housing. And then we minimized the size. Our proposed design that we've done thus far is actually 5 times smaller than the VA initially proposed design. We wanted to make it with biocompatible materials. We have not been able to achieve this due to funding. However, it's very achievable. We wanted to make it user-friendly. This was achieved by adding the alignment pins in the housing. And then test for continuity and hermeticity. We tested for continuity. This was successful. Hermeticity, we have been unable to test because we do not have the final housing completed. Now for the cost analysis, the total cost for the prototype was $56, with the bulk of the cost coming from the graphite. If you actually went with the biocompatible, you'd be looking at over $500 for the micro connector, with over 80% of the cost coming from the fuzz buttons and from the platinum paste. And to discuss our project timeline, Brian Martha.
So this is the timeline of our project and the responsibilities. You can return to these slides if needed. So for our global component, we wanted to investigate the environmental impact that our part would have. We used ceramic for both the male and female half, and unfortunately ceramic is not biodegradable. However, as you can see in comparison to this quarter, our waste material is very, very minimal, and should we mass produce it, our waste could be reduced. We also wanted to create a general awareness for our connectors that would solve an international engineering problem while setting the foundation for a device like this. Upon making it biocompatible, we would submit it to the FDA, which would use military test standards to test our device, as well as the EMA, which uses ISO 10993 standards. So we also wanted to make a micro connector that was as cost-effective and sustainable as possible, because as I mentioned in the beginning, there's only 50,000 neurostimulators implanted worldwide annually. So this is a very viable market. Overall, we were able to fix various issues that we encountered in our design, one of them being the alignment by adding pins on the housing. This would make it very accessible for the doctor to assemble in the operating room. We also were able to improve the manufacturing process by eliminating screen printing, and we added a strain relief to protect the stimulators. We know that a biocompatible microconnector is possible to make as long as the funds are there. However, we do need further research and testing. We can conclude that with our limited resources, we were able to successfully make a microconnector with 32 connections, which doubled the output of what is now commercially available. And this is a technology that is very new, and we were able to accomplish doubling the output. So overall, we want to give a very special thanks to the brain of our project, Dr. Jones, and we couldn't do it without Dr. Carvazzi, obviously. From the people present here, Mr. Ziccarelli for all his advice, Dr. Basil for allowing us to use the 3D printer, and Omar.
All right.
For questions, we wanted to show you our senior design project. It's really small, so you guys could pass it around.
All right, in the meantime, are there any
This
questions?
is basically the housing.
Good question.
Yes, Dr. Bill Krantz and
I
Dr.
did
Tremonti.
I did not get the understanding what exactly is the stimulator doing. Is it stimulating electric field? Is it stimulating magnetic field? What is the connection between the electrodes, this stimulator, and the brain tissue?
Well, what it is a neurostimulator is connected to the leads, which has the pad. The pad is what actually connects to the nerves.
Speak up. Excuse me.
The lead, it connects to the neurostimulator, and at the end of the lead is the pad. The pad is what actually attaches to the nerves.
So again, is this stimulator with the electric field or with the magnetic field?
Electric.
Is it steady or is it unsteady?
That we didn't get into.
I'm getting into engineering issue here.
Okay.
Do we have any joule heating here?
We did not analyze that. Our primary objective for this is just product development and proof of concept.
We wanted to test the manufacturability of this device because this is something that hasn't been done at all. So just in itself, no one knew if we could double the amount of connections, and just that alone is a feat in itself, just because this technology is very new and it's limited. So we weren't able to test many of the engineering questions that come up. We were really focused on manufacturing it.
So there's a scope limitation.
Yes.
Dr. Tremont.
My question, guys, tolerancing. How precise can you make the pins and holes?
Well, the pins and holes, what we made is, it was 6 microns. We actually have a smaller punch, but what we did right now is 6 micron for, 6 mils for the pins and then 10 mils for the female.
Okay, how precise can you make the polymeric frame that you're sticking around that structure?
Ultimately, we would need to do a mold because we just did the 3D printed for cost effectiveness as far as attaching the microconnector with the housing, how to fit within.
Okay, but the guides that drive the pins into the holes are dictated by the polymeric part. Is the precision of the polymeric part adequate to ensure that all of those pins are going to go in all those holes?
Yes, it's very capable. The one thing that would have to be done as far as the pins goes, those would need to be cleaned up probably from a chemical etching so that you have a much smoother surface as opposed to some of the rough edges that you've seen in our pictures.
Clear, right? Crosstalk. Is there any crosstalk between these pins?
That was not analyzed because number one, currently for the prototype, it has to be made in silver because of the burn rate. The melting point of silver is below the HTC, the LTCC. For the final product, it would need to be in platinum with HTCC.
Okay, then my very last statement. In the environmental section, you talked about the ceramic not being biodegradable. Well, I would hope it wouldn't be biodegradable,
Oh, yeah.
considering the fact that you're putting in a neurostimulator that's holding the body.
Yes, the alumina is biocompatible, and obviously it's not biodegradable.
Okay, thank you.
All right, any other questions? Yeah.
What about shrinking and expanding of the polymer itself when it's in the body? Then, so the tolerance would change.
We weren't able to test for things like that because we first manufactured it in LTCC, and ultimately it would be in HTCC, so we haven't yet explored those options.
And that would have a big thing to do with the actual biocompatible plastic that would be chosen for the housing, which we haven't gotten to. Because there's so many different types of plastics that you get, and they all react differently to when they're molded and how they're molded.
So that would be.
That's something that would have to be investigated later on, once it goes into production.
And you said you did a continuity test?
Yes,
Correct.
just to ensure that we had a connection between the male and the female.
So they worked for all pin connections? How many pin connections?
Well, we only inserted the 6,
Okay.
so we tested for
All
those 6.
6 worked for?
Yeah.
Okay.
That's it, Dr. Basil?
Yep.
Just to piggyback on Dr. Basil's question, have you mapped out future steps and actions that needs to be taken in order to bring this to common use?
It would have to be done in conjunction with the VA as they've already started the research on it and developing the prototype. The one thing that we do not know, for example, is the current that is given from the neurostimulator. A lot of the information from that is highly technical, and we were unable to get that from the manufacturer. So, but as far as further development, you'd have to work in conjunction with the VA and developing the test protocols necessary.
Okay. Any other question? Hearing none, thank you so much.
One comment I would say, no one's ever developed pins in this technology.
I'm sorry?
No one's ever developed pins in this ceramic technology.
So that's what's new.
And that's what's new. And
Yeah.
so, as I said, we're going to be actually moving this into getting funding from the VA to start this summer, going into the HTCC. And then the design team for the VA will end up designing this, use this and optimize it, and then we'll end up making parts. They're already making, the VA is making the strain relief system for us.
So could this be a future final design project? The next steps, next phase?
But by next step, hopefully, this is the hard part. This is what we couldn't figure out we could do.
Okay.
So,
One comment that I may make, with this kind of technology that.
Could you introduce yourself?
My name is Ali Kabasi, I help lead this
Okay.
project. But with this kind of technology that they did, they can increase the number of connections. Now they work on 32, but they can easily increase it to 200, for example. So that's not going to be a problem for the future as well.
We developed for the VA and delivered almost 100 devices that have 332 pins in them in a 7 mm diameter, completely hermetic to 10 to the -9th of the mill standard. And so we had to develop all the materials for that. So we understand what we have to do with the alumina as the next step. But we prototyped that also in LTCC, and that was what we wanted to do, have the students do. Because the processes are very similar. If you can't get the processes to work, it doesn't matter if you have the materials in.
Okay, beautiful. Thank you for the additional comments. Any other questions or comments? Hearing none, thank you so much.